Which exam was it?
Chapter 14.
The B or C version? C. All right. What number?
Number 2.
Number 2. Okay. Number 1 and number 2 deal with acid strength, and those aren't going to be on this test. Tomorrow we're going to do an acid strength lab, so you don't have to worry about that.
What about 3 and 4?
3 and 4 will be on the test. 3 is a mechanism. What is a mechanism? Yeah, it details all the steps that are involved in the reaction, and those steps are called simple collisions. So that's true.
So what about 4?
3 molecule collisions are the most probable.
Oh, I mean, that's false, right?
That's false. 2 molecule, or which are called bimolecular, are much more probable.
You posted these, or?
I didn't post them, but somebody else posted them. Let's see, James posted them Friday.
What about 5?
Number 5?
Yeah.
When ozone undergoes a unimolecular collision, the most likely products are, could it be A? A's not possible. A's impossible because, ozone goes to O2 plus, O2 minus plus O is not possible. Because of charge balance. Here, the net charge on the left is 0, the net charge on the right is -2, so all of a sudden we came up with 2 extra electrons. If we had 2 electrons, let's say 2 electrons plus an ozone, then it might be possible. Because then we have the 2 negative charges here, the extra 2 electrons. But there's no 2 electrons here, and those electrons have to come from somewhere, And so this is not possible. A is not possible. B is possible. So if ozone goes to 3 atomic oxygens, it's possible. All the bonds are broken. So we just have the atoms. It's possible. C. C is not possible because it's not balanced again. If we have an ozone with a positive charge here, there's got to be an electron out here somewhere to balance it out. And so because of charge balance, it doesn't work. So this one doesn't work, that one doesn't work. Because it's not charge balanced. D. What do you think of D? Goes to an O2 and a O. Does it make sense or not really?
Because oxygen can be not diatomic. Okay?
Yeah, it can. We call it atomic oxygen. Yeah. Atomic oxygen. It doesn't want to be atomic oxygen. It doesn't want to be atomic oxygen because it has less than an octet. So it either wants to take 2 electrons or it wants to form 2 bonds. Right? But in this case, O2, is O2 good? O2 is good. I mean, we form molecular oxygen, and then O is not good. O is going to be reactive. But then again, ozone, is it very stable? Ozone is not very stable. Ozone is inherently unstable, so ozone is very reactive. And so actually, this is a possibility too. An O2 and an O. How about E? E goes to an O plus an O2 minus plus an O plus. This is okay because the charges are balanced, but compare this one with this one. Which one is more stable? The first one is much more stable. One way to think about this is if you had a tug of war for electrons, which oxygen would win? If 2 oxygens were in a tug of war and they're trying to pull on the same electron, which oxygen is stronger? The left oxygen or the right oxygen? Or in this case, the middle oxygen, the left oxygen, or the right oxygen? Which one is the strongest? Well, it looks like the middle oxygen is the strongest because the middle oxygen was able to take an electron from this oxygen and this oxygen. So these two oxygens must be weaker. This oxygen must be much stronger. But what makes this oxygen much stronger? Well, nothing, because all the oxygens are exactly the same. So if all the oxygens are the same, then this is very unstable, right? If you had a tug of war, it should be a tie. You know, it shouldn't be like this. And so this one doesn't look good. So it's between these two. Which one do you think is more stable? This one or this one? This one?
The first one?
The first one? Why do you think this one's more stable?
Because we don't have knowledge of that.
We don't have what?
We don't have, well, the third one has diatomic oxygen and atomic oxygen, so it makes it less stable.
Well, okay, let's remove the atomic oxygen. When you breathe air, do you breathe atomic oxygen or do you breathe diatomic oxygen? Why do you breathe diatomic? Why don't you just breathe two oxygen atoms? I mean, when we're breathing air, I mean, why isn't it just atomic oxygen?
It's very reactive.
Yeah, atomic oxygen is very reactive because it's got less than an octet. It's got 6 electrons, valence, and it wants 2 more.
Isn't that a free radical?
It's a free radical. They call these free radicals. Free radicals are what we call dangling bonds, or, you know, they want bonds. They got unpaired electrons. They want a bond. And so in this particular case, this one has an option to form 2 bonds, or has an option to gain 2 electrons. But gaining 2 electrons, they'd have to take it from 2 oxygens, or 1 oxygen goes plus 2. I mean, there are other options here. We could have 1 oxygen lose 2, 1 oxygen gains 2, and the other oxygen just breaks even. Does this look very stable? And this looks even worse than this, right? Or we could have something like this. We could have, these are kind of high charges, so maybe if we did this. Well, anyway, these aren't good, so we're looking at this. So what do you think is more stable? 2 atomic oxygens or diatomic oxygen? Diatomic, so it's this one. This would be it, because, you know, this, even though none of these are very stable, right? The most likely one to form would be the most stable one, and that would be O2 plus now.
What does it mean by those unimolecular collision?
What does a unimolecular collision mean? It means it's a 1 molecule collision. So how do you have a 1 molecule collision? Is that even possible? Yeah, right. The ozone can collide with a wall, or it could collide with an inert molecule like a nitrogen. If we have ozone in air, then it can collide with the nitrogen molecules in air. It could even collide with the oxygen molecules in air, but that would probably lead to some kind of reaction.
Well, that wouldn't be unimolecular.
Well, yes and no. Because a wall is not part of the equation here, nor is an N2, because N2 doesn't lead to any product, a wall doesn't. And so it's unimolecular. Like, if you're a single ozone and you collide with the wall, what would you call that collision? You'd call it unimolecular for the molecule, but what would you call the wall? Do you see? If the ozone collides with the wall, should you call it unimolecular? I guess there's really no such thing as a unimolecular collision then, you know, in that sense. The reason they call it unimolecular is because there's only 1 ozone molecule involved in that collision. The collision requires 2 species. It's just those other species of walls. So don't know what you'd call it. You know, ozone plus wall, or ozone plus nitrogen. And so in this case, the wall's stationary. It doesn't have to collide with anything, but the ozone collides with it, breaks it apart. Okay. All right, other questions?
Number 11.
Okay, if we look at the, what's that graph called? Hmm? What's the name of that graph there?
Is that a reaction profile?
Yeah, reaction profile, or reaction coordinate diagram, or the reaction progress diagram. So what it does is just spreads out the energies, and then you can see, you know, the progress of the reaction in terms of energy. Yeah. And so we use that to answer those questions there, like number 11. What is it? Did you figure out number 10?
My practice test looks different from this.
Oh, okay. Number 11, is a single molecule unimolecular collision possible?
No. Yeah. Is it? Is that would that be the elementary?
Yeah, well, yes and no, but I mean, if you have a collision, you need collision between molecules, but
But I thought the first one was no collision at all because we only have one product turning into, I mean, or
one reactant?
Yeah, turning into a product.
No, there's got to be a collision.
Okay.
There's got to be a collision, but they call it unimolecular because can I have a collision with a pen? I have one pen. Is it possible to have a collision? Well, not really, but if I threw this pen at the wall, then what would you call it? Would you call it a single pen collision, or what would you call it?
Single pen being thrown into the wall.
Single pen being thrown into the wall. Okay, then unimolecular would be the same thing, because if there's an ozone molecule being thrown at the wall, it's the same thing. It's a single ozone molecule being thrown at the wall, which would be, you know, if you throw it hard enough, it's going to break. Just like if I throw this pen hard enough, it'll break, or the cap will come off, or something like that, right? And so, well, that's what we're going to call unimolecular. Yeah, it's a single pen. So uni, it's just one. And single molecule, it's one molecule, but it's colliding with a wall, which... And so in that sense, it's possible.
Is that the sense?
But, you know, it could also collide with something like a nitrogen molecule.
Well, that would be the bi.
It would be bimolecular, but we don't call it bimolecular. We still call it unimolecular because nitrogen would be considered inert and not part of the reaction. And so whether it's a nitrogen molecule or the wall, we still call it the same thing, unimolecular. Even though technically an ozone with a nitrogen would be a bimolecular collision. We just don't call it bimolecular because the rate, we make an assumption. We assume that the nitrogens are plentiful. You know, there's lots of nitrogen. So it's not really, in other words, it's going to pseudo M order itself out. There's just so much nitrogen that it doesn't really change the concentration. Uh-huh.
Can the catalyst also lead to unimolecular collision?
No. No. Well, it depends on what the reaction is, you know. Like the enzyme catalyst would be unimolecular. You know. Even though it's unimolecular, the catalyst is a little bit different because the wall, you know, the wall is not going to impact the rate because you know, we have a lot of wall here. Or nitrogen is not really going to impact the rate because there's lots of nitrogen. But a catalyst will, because a catalyst is present in limited quantity. You know, you want to dump in enough catalyst, it doesn't limit the reaction. And if that's the case, then it'd be like unimolecular, you've got plenty of catalyst. But if you don't have enough catalyst, then it's going to slow down the rate. And so let's say it's the same thing with the wall. Usually the wall we don't factor in there, but let's say we get rid of all the walls and just put a pole in the room. Then all of a sudden the number of collisions between ozone and the walls are going to be greatly reduced because we have no walls. We got this little pole in the middle of the room and it's totally empty. Then the number of collisions goes way down, and then all of a sudden it's going to depend on something else. And that's something else that we have to factor in. And so in enzyme kinetics, it's, or just any of those. Here, let's take a look back here. The catalyst is consumed and then it's spit out. But the catalyst is important because for every formic acid, we need one H+. And so the catalyst is going to have an impact on this. And so in a sense, this particular reaction, because it has a catalyst here, is bimolecular. Because the H+, if we don't have enough catalyst, now if there's so much catalyst that we can do pseudo-M order, then it'd be unimolecular, right, in terms of formic acid. And well, that's the same thing. If we have a wall here, or if we have lots of nitrogens, then it's going to be unimolecular. But all of a sudden, if this goes down to this, a single ion, then it's going to be very important that we have enough. So if we don't have enough, then it's going to slow down the rate. So let's say we don't have enough H+ for every formic acid, then the rate is going to be slowed down by the amount of H+. If we double the H+, then we should double the rate of reaction because we'll be able to react with twice as many formic acids. And so in catalysts, what we see is this. We see a dependence on how much catalyst. Catalyst is E here. And so it's first order in terms of the catalyst, but once you hit a certain point, that is, let's see, once the reactant concentration gets so high that limits the catalyst, doesn't matter. So with catalysts, it's a little bit more complicated, I should say. And the catalyst will make it a bimolecular process. You can see it more easily here. I should have done it with the hydrogen peroxide here. You can see, normally hydrogen peroxide becomes, you think is unimolecular, hydrogen peroxide goes in water and O2, but in this case, or maybe it's more complex, in this case with the iodide here, which is catalyst.
Professor, what's the pseudo-M order?
A pseudo-M order is if you make the catalyst concentration so high that it's essentially constant. Catalyst is tricky because the catalyst concentration is essentially constant, right? Because it gets consumed and then it's spit out again in a cycle. And so it gets consumed and then spit out again. And so essentially the initial concentration and the final concentration of the catalyst is the same, but during the process, no, some of the catalyst is consumed in the particular reaction. But in typical pseudo-M order, you make this so big, it becomes a constant, and it only depends on the hydrogen peroxide. All right.
Wasn't the bulk?
Number 12?
Yeah, it only depends on concentration rates. Is it never?
No, reaction rates depend on temperature too, because of K. If we look at K, the rate constant depends on A, e to the minus EA over RT. You don't have to memorize these equations. All the equations I'm going to give you. Some equations you might have to derive, like for example, a half-life equation or something like that. You have to derive. But when we look at the rate constant is going to depend on the temperature. So if I double the temperature here, will the rate constant double? That's the question here. Well, I'm not doubling. I'm only increasing the temperature by 10 degrees C. So if I increase the temperature by 10 degrees C, will the rate constant double? It doesn't look like it would, but well, let's take a look.
Professor?
Uh-huh.
You said we might have to derive half-life?
Yeah.
Maybe for all three? Or you can ask us specifically for one?
Well, you know, one or all three, it's pretty, well, we'll do it right after this.
Okay.
It's pretty much the same process. So if you could do the half-life for first order, you could do the half-life for all of them. But let's take a look at this. Yeah. All right, there was a problem in the book. I can't remember what number it was. Homework problem. Asking about this. So, is that possible? Well, there used to be an old rule of thumb. This applies to cooking. If you increase the temperature, you know, by plus 10 degrees C, then the rate doubles. Have you ever heard that? You know, just a 10 degrees C temperature increase will speed up the reaction quickly. And so, is that always true? Well, if we look at this, we could figure something out, because it's going to depend on something else in this. And so if the rate doubles, then we could say this: K at temperature plus 25 degrees C versus K at temperature is going to equal 2, you know, because this will be twice as much this and it'll cancel out, right? So we double the temperature. And then this is going to equal AE to the minus EA over RT divided by AE to the minus EA over RT. And so we'll call this temperature 2, we'll call this temperature 1. Here. And then we'll solve this. Well, the A's end up canceling. But the EA's are a different story. And so when we do this, this is going to equal E to the minus EA over RT2. Okay, then we change the sign. This is going to be a minus. Oops. A minus EA over RT temperature 1. And so this is going to equal E, and we'll factor out the minus EA. This will be over R. This would be 1 over T2 minus 1 over T1. And then we take the natural logs of this. And it turns out that this can be made true at one specific value of EA for a given T1. And so it depends on your initial starting temperature. So let's say we start at room temperature, we increase it to room temperature plus 25 degrees C, then it's going to have an activation energy that's going to be about 60 kilojoules per mole. And so 60 kilojoules per mole of activation energy will mean that for every 10 degrees C increase in temperature, the rate doubles. But a 60 kilojoules per mole activation energy, is that very much energy? You know, 60 kilojoules, give me a feeling for, you know, that in terms of bond energies. Well, 60 kilojoules can heat up a lot of coffee, but in terms of bond energies, it's not much, because the weakest bonds are going to be about 100. Strongest covalent bonds are about 1,000. And so it's not really enough to break much bonds. So usually, you know, with an activation energy around there, you're just looking at denaturing proteins, you know, breaking the hydrogen bonding interactions and all the foldings and that kind of stuff. So just cooking food, maybe breaking some of the weaker bonds. With a carbon-carbon bonds like 400 over 400 kilojoules per mole. You know, an oxygen-oxygen double bond is between a single bond. Single bonds are around 400 kilojoules per mole, 350, 400. Triple bonds are 1,000 kilojoules per mole. And so it's just not that much energy. And so if you have strong bonds, what it means is a 10 degrees C temperature increase is not going to double the rate. The rate will go up a little faster, but not nearly that much faster. This is actually a homework problem. I forgot which one it was. But part of a homework problem that is figuring out, I think that is figuring out the activation energy. this.
So how much temperature increase would the rate?
How much?
Like about how much?
10 degrees C. 10 degrees C will double the rate if the activation energy is around 60 kilojoules. If the activation energy is higher than 60 kilojoules, you're going to need more temperature increase. If the activation energy is lower than 60, then it more than doubles. Okay. But that's the starting temperature. You have to assume some starting temperature. So this one comes from this particular problem. May seem very tricky, but if you reference the homework problem, then it's not that bad. And so if you reference the homework problem, then the answer to 12 is C. It's possible at a given temperature, initial, and a given activation energy, then it is double. I was looking for the specific homework problem, but I didn't see it. It's in there, though.
Would 14 be B, intermediate?
Yeah. 14B is correct.
Why is it not A?
Why is it not A? What do you call B here? Because B is not D. D is the ultimate product here. So is B an intermediate or is B a transition state? B is an intermediate. Where is the transition state? The transition state is some kind of transitory state in going from A to B that's here. It's not shown here, but it's at the top of this peak. And at the top of the peak is where the bonds are being broken and the new bonds are being formed. That's a transition state. And so here, this intermediate, and then the others will be transitions.
Would the intermediate step be the fastest, or?
Well, here, we could answer the questions related to this one. Which is the fastest step in this particular reaction? The BC would be the fastest because BC would be the smallest hill to climb. Which is the slowest step? AB. This is the biggest hill to climb, going from A to the top of that peak versus C to the top is a little smaller climb. And so if you're, if you're a group of bicyclists, then this would be the one that would spread people out. Most people would get over this fast. This would be a little faster than that. How many intermediates?
2.
2. B is an intermediate product and C is an intermediate product. How many transition states? Actually, there are only 3 transition states here. Transitioning from A to B, we go through this peak, so that's 1. And then from B to C, we hit this peak, that's 2. And from C to D, this would be the transition state here. So there's just 3 transition states.
So the peaks would be transition.
Yeah, at the peaks would be the transition state. And so, we might see that. As these two collide, then we're going to transition through a state where the bonds are breaking and the new bonds are forming before we get to the final product. And so at the peak, the transition states, it's a little bit of guessing, what it's going to look like. It's going to be Like in the lab we're doing tomorrow, Spartan has an option where you can think up a transition state like this and then calculate its energy to see, you know, is that a reasonable transition state? And then think of other options for transition states and then calculate the energy and see which transition state seems to be most likely to occur, the lower energy path should be the more likely to occur. Is the overall reaction endothermic or exothermic? It's endothermic. You know, you start off at A here, you end at D, and so there's a net increase in energy, so it's endothermic.
Go back to the previous.
Okay.
For 15.
Uh-huh. All right, so we have some rate law for this reaction A plus 3B. You look at the coefficients 1 and 3. So does that mean N is 1 and N is 3? No. In fact, it's likely not the case because this would be a 4-molecule collision. Are 4-molecule collisions very probable? No. And so here, then if M is not 1 and N is not 3, then where do M and N come from? Well, that's how you can determine them. But determining them is not, you know, where they originate from. Where do they originate from, you know, like theoretically? They're the order, we call them the order reactions, but, you know, that's just what they're called. Where do they come from? Theory would be like a descriptive picture of where M and N come from. Right. Right. They're going to come from the mechanism of the reaction. In fact, M and N are a result of the molecularity of the slowest step in the mechanism. And so what we see here is there could be a multi-step, and in fact it's likely there's a multi-step mechanism in here. In that multi-step mechanism, there's going to be one slow step. In that one slow step, it's going to depend on collisions of either these or intermediate products. But whatever it is, you know, we're going to see how the species in the slowest step, you know, how their concentrations are impacted by the original reactants here. That's what we do. So we do, for example, if the slowest step is the second step, we'll do the fast reversible or the steady state approximation to see how the species involved in the slowest step concentrations depend on the original. Okay, and that gives you the molecularity. Okay, so the answer is from the mechanism, you know, from the slow step in the mechanism. That's where they originate from. Okay, other questions from?
How about number 9 on the other test?
Number 9 on the other test. Okay, in enzyme kinetics, at very high substrate concentrations, the reaction is 0 is correct, yeah.
Why is it 0?
It's 0 because, let's take a look at this again. Here. Well, what order enzymes, the catalyst, And so this is it. We need enzyme for this reaction to occur. The substrate's the reactant. And so if we have plenty of enzyme, then if we double the substrate, we should double the rate of reaction. That's like this. You know, they used to use the phone booth analogy, but it's less applicable nowadays. There's no more phone booths, but you know pay phones?
There's phone booths in London.
Okay, phone booths in London. So let's say there are a whole bunch of phone booths, right? If there are a whole bunch of phone booths and not many people want to use them, then you look at the number of calls. So if there's one person making a call, then that's the rate of 1. If you double that, you get 2 calls, right? 2 callers. Triple that, you get 3 callers. So it's first order in the number of, we'll call the callers the substrate. But eventually what happens is, what if everybody wants to make a call at the exact same time? Let's say there are only 10 phone booths, but there are 20 people who want to make a call. Okay, then what we've done is we've saturated all the phone booths. There's not enough phone booths, right? And so what if we double the number of callers? Let's say we go from 20 people who want to make a call, now 40 people want to make a call at the exact same time, but there's only 10 phone booths. Are we going to double the rate? So we doubled the number of callers. We should double the rate of calls, but we didn't because there are too many callers and not enough phone booths. And so that particular question is the exact same thing. The enzyme is like the phone booths. What number was that again? So the enzyme is the same thing. At very high substrate, so what that means is the enzyme's like the phone booths, but we have too many callers, which is the substrate. When you have too many callers, if you double the number of callers, is that going to have any impact on the number of calls you make? No, so we call it zero order. Zero order has no change. You still can only make 10 calls at a time because there are only 10 booths.
Because it has to match the constants.
Right, or for zero order. For zero order, you can see it here in the graph. Take a look at that. Here. And so here we have plenty of phone booths. So if I double the number of callers, I'm going to double the number of calls. Quadruple the number of callers, I'm going to quadruple the number of phone calls. But eventually I'm going to hit this point where no matter how many times I double this or quadruple this or tenfold increase, I only have this number of phones. And so if I only have 10 phones, then it's going to plateau there. I can't make more than 10 calls. No matter if I make, let's say I had 1 million people trying to make a call, and then I went to 1 billion, that's going to have no impact on this because I can only make 10 calls at a time. And so that's why it flattens out to zero order. Here it is in zero order. It's first order when I have plenty of enzyme, you know. I can double the number of substrate and double the rate of reaction.
What would second order be?
We wouldn't have second order in that particular situation. But second order is like this. Let's assume I have plenty of the right one. So if I double this, then if I double the left NO, I'm going to get twice as much NO. If I get twice as much NO, then I'm going to expect twice as many collisions. Well, if I get twice as many collisions, I'm going to have double the rate of reaction. There's twice as many collisions, right? But the problem is I can't double the left NO without doubling the right NO because they're the same thing. It's NO. And so if I double the left NO, I double the rate of the reaction. But at the same time, if I double the right NO, I'm going to double the rate of reaction. If I double both NOs, I'm going to quadruple the rate of reaction, and that's what we see. You know, that would be second order. Second order is when it's the same thing. Whereas this is different because this is like something else here, but if it were the same thing, then it would be second order, you know, in that particular case. Okay. Other questions?
Are you gonna derive half-life?
Okay, the half-life, yeah. So I'll give you all the integrated rate laws. The rate laws you should know, because those are pretty straightforward. And so for the half-life equation, T1 half, you know, we did do it for our different ones. The most common is first order. The reason first order is most common, there's an equation in the book that talks about the T1 half for first order reactions. But here, if we look at this, what we want is we want the time it takes for the concentration at time t to become 1/2 the initial concentration. And so we know from the integrated rate law that ln of A at time t over A initial is equal to minus kT. So if we solve for the time it takes, the time is just going to be the ln minus the ln of time t over initial over k. And then we could just plug that in. This is going to equal minus ln. Okay, the concentration at time t is equal to 1/2 the initial. So this is going to be 1/2 the initial concentration over the initial concentration divided by k. Here, the initial concentrations cancel out. And so this gives me minus ln of 1/2 over k. Natural log of 1/2 is negative 0.693, so it's negative times negative, which is going to give me a positive. So this comes out to 0.693 over k. And so this equation is given in the book, but it's a simple equation to derive. In fact, you should know how to derive this because, you know, I could ask you a question like this. Maybe not half-life, but I might ask you like this. How long for 99% reaction? And so T for 99. This is T for 50% reaction, right? How would you do T for 99% reaction? Well, it would be the same kind of calculation. That is, you know, T is the question mark, but we know the concentration at time T should be we should only have 1% left. And so that should be 1% of the initial concentration that's left if 99% of it's reacted. And so then we can do the same thing. This is going to be ln of concentration time t, which I'll just plug in. I'll skip a step here. 0.01 times the initial divided by the initial. So the initial concentrations cancel. So this is a natural log of 0.01 divided by k. So this would be 99% reaction. This is 50% reaction. We should be able to do this calculation for any percentage, right? And so this is why I'm not going to give you this equation, because this is just a standard calculation. You know, how long does it take? But for first order, you can see that first order, k is a constant, and so the T1/2 is a constant. But for zero order, it's not. I mean, if we did zero order, to figure out the T1/2, we could do that. We know for zero order reactions, does the half-life decrease or does the half-life increase? It decreases. And it actually decreases by half each half-life. And we could actually derive the equation that dictates that by just saying, you know, how long does it take for the concentration at time t to be 1/2 the initial concentration? And so we just plug that into the integrated rate law. The integrated rate law just says that the concentration at time t, well, we'll just solve it for t. If we solve it for t, that says the concentration at time t minus the concentration initial over K, just multiply that, is equal to the time. It's -1. And so we know the concentration at time t is just 1/2 the concentration initial. So this would be 1/2 the concentration initial minus the concentration initial divided by K. And so that's a minus of 1/2 minus 1, which is going to give me a +1. This is going to be +1/2 concentration initial. The concentration initial doesn't cancel out in this case. And so the T, the time it takes, depends on what your starting concentration is. And so if we cut down this, then it's going to be half as long. Each time we cut this by half, we've got to cut the time in half. And so each successive half-life is half as long as the previous. Whereas for, for second order, it's the inverse relationship. So it's going to be double, the time. Yeah. But we could do the same thing, 99. If we had second order or zero order, how long does it take for 99% reaction? We could figure it out based on the integrated rate law.
How will you do the 99% for zero order?
For zero order, how would they do it? I would just here, the concentration at time t should only be 0.01 times initial. We should only have 1% left. And that means 0.99 was eliminated. And so this is the final concentration. This is the initial concentration of 1. That's the way we do it. Or we could just plug it in. If we had some numbers, we could just plug in the numbers. Let's say the initial concentration was 1.54%. So what is 99% of that? Or what is 1%? 99% of that is what we lose. And so we only have 0.01% or 1% left. 1% of this is 0.01 times that. So it would just be 0.01 would be 0.0154. Final concentration, something like that. Or no, I mean molar. Does that make sense? That's the way we do it. All right, other questions? Oh. This one? 13 says highly exothermic reactions have negative activation energy. So it's highly exothermic, so delta H negative, so we're going down, it's exothermic. And so if it's highly exothermic, is the activation energy negative like that? This would be a negative activation energy. No, actually it would go, yeah. Yeah, we got to break the bonds. Even though, when we form the new bonds, that'll more than make up for it. But initially, you got to break the bonds. And breaking bonds always costs energy. And so the same thing, methane and oxygen is highly exothermic, but no reaction is occurring here because of the activation energy, breaking the bonds. It's slow.
For zero order, if you double the concentration, would the time double as well, or would it get
the half-life? Yeah. It'd take twice as long to decompose half of it. Okay, other questions? So highly exothermic have negative, yes, that's false. Then if activation energy is breaking bonds, then there's no exothermic. It's going to be, unless the bonds are much weaker than the element. I mean, there are cases where maybe, but it'd be, something very, very unstable to begin with. Okay, are there any other questions on the chapter 14 stuff? No?
For number 10 would be D.
10. 2A goes to product. The rate is where M is equal. Yeah, not enough information because you don't know if that's a single step. If that were a single step, then it would be true. But since you don't know that, then it could be false. So not enough information. We don't know if it's an elementary step or a process. If we were told it was, then it'd be true.
What is the frequency factor?
Frequency factor? Frequency factor is just how frequently do we get a collision that has the correct orientation, let's say. A, the frequency factor of the pre-exponential. And so if it's very frequently that we get the collision with the correct orientation, then A is big, and therefore K is big. But if it's very rare that we get the correct orientation in a collision, then the frequency factor is small and K is small. The rate is much slower.
So the frequency factor is just the concentration?
No, the frequency factor is going to be related. Let's say the concentration, let's say you have 1 molar versus 2 molar. And let's say, as far as the percentage goes, 1% of the molecules have the correct orientation when they collide. And so the frequency factor is not, if you have 2 molar, right, it's not quite, it's going to be a proportion, it's still gonna be the same percentage, in other words, of molecules. So let's say 10% have the right, and so it would be 10% of 2 versus 10% of 1. But the concentrations come from this. And so 10% of this would be it. So if you double the concentration, the frequency factor stays the same, but the rate of the reaction increases. Because now you got a lot more molecules. 10% of 2 molar versus 10% of 1 molar is a lot more molecules.
If you double the concentration, why would you use the frequency factor?
No, frequency factor stays the same because if you have 100 molecules and only 10 of them have the correct orientation, then that's 10%, right?
But if you double it and it becomes 200, then that means that 20 becomes.
Yeah, but it's still 10%.
Oh, yes.
And so the frequency factor is the 10%. It's a,
So number 9 would be all of them except for A?
the rate constant depends on, yeah, all of them except for A.
Why is it except for A? Wouldn't it depend on the concentration as well?
K? No. K, the concentrations are kept separate. And so when we look at the rate is equal to K, A to the M, B to the whatever. And so it's kept separate from concentration. If A depended on the concentration, if K depends on the concentration, then we'd have to figure out a K for every single concentration you're doing, which is awful because the concentration is always changing, and therefore Yeah. Well, it's a lot easier to do it this way. Okay, are we done with the questions? Yeah. All right. Did we change? Did we look at changing the temperature on delta G last time? Yeah. Did we do a temperature calculation with that?
Very little error. Yeah, so it's basically delta HT over delta S.
Okay. What was the reaction we were looking at?
Two nitrogen monoxide
Goes to 2 NO2s. All right. So we calculated delta G for this. What?
No, it has like T. Delta T. Sorry.
Okay. What was delta G for this? Which means it's spontaneous. Negative 70.4 kilojoules, spontaneous. All right, then what we're going to do is we're going to see, you know, temperature can actually influence this, because when we look at delta H, was delta H exothermic or endothermic? And then delta S, did we have these numbers, the delta H number for this and the delta S number? Oh no, before that. Before that.
We didn't have values for those because we assumed that it was. It wasn't
All right, maybe let's go back and we'll take a look at the delta H and the delta S for this. We'll go to appendix D. But the delta H calculation for this should be straightforward. If we use the, you know, the sum of the delta H's of formations. Yeah, so I'm going to back up just a little bit and then just review some of this. See, I can't scroll down on this. It's not letting me scroll. Okay, fortunately I have it here. I don't, shoot. N2O. Is there N2O in the book? Page 821? Oh, no, NO. Sorry, not N2O. I have it here. Is there NO in the book? Yeah, nitrogen monoxide. Let me do that delta H of formation.
That is
90.35?
25.
25 kilojoules per mole. And NO2? NO2, I can see it here. 33.18. And O2, everybody should know what O2's delta H of formation is. What it should be 0. All right, and so we could calculate our delta H. The delta H is going to be the sum of the delta H's of formation of the products minus the sum of the delta H's of formation of the reactants. Do you remember doing that kind of calculation? And so we have 2 of these, and so this is going to be 2 times 33 or 2 moles, I should say, keep track of the units. 2 moles times 33.18 kilojoules per mole, and that's going to give me how many kilojoules are from the formation of NO2, minus the reactants. And so now I have 2 moles of NO, and that's going to be 90.25 kilojoules per mole, NO. And then I have 1 mole of O2, so it's just 0 for that. And so we can figure out what this is here. I was figuring this is going to be exothermic because this looks like a combustion reaction, right? We're burning NO to form NO2. And so it's just completely combusting. So what does the delta H for this come out? Negative 114.14. Okay, the units would be kilojoules. So this is favorable, right? We want to minimize energy, so we want delta H to go down. So this should be good for driving force. Well, what about delta S? Delta S is going to be the entropies. And so when we do the entropies, they're the absolute entropies. And so I know delta H of formation of O2 is 0, but would the absolute entropy of O2 be 0 also? No, it's not the case. So let's do the nitrogen-containing species first. What is the absolute entropy of NO?
210.
Okay, the units would be joules per Kelvin mole or mole Kelvin. And the NO2? NO2 would, well, let's stop here. What do you think? Would it have a higher entropy than NO or lower entropy than NO? It should have a slightly higher entropy because NO is diatomic. NO2 is triatomic. And so if we have a triatomic, we have more vibrations and rotations that are allowed. And so NO2 is going to have more ways that you can arrange the atoms than just NO. But they're both gases. All these are gases, so they should have one. So I would expect NO2 should have a slightly higher entropy than NO just because it's triatomic versus a diatomic molecule. And so what is the entropy of NO2? 240.1 joules per mole Kelvin. And then we have to go to O2, find O2 entropy. 205.1 joules per mole Kelvin. And then what we do with this is we just do this. Delta S is just going to be the entropy of the products minus the entropy of the reactant. Entropy is extensive as well, and so we got 2 moles of NO2 times 240.1 joules per mole Kelvin, so the moles cancel out there. Okay, minus the reactants. And the reactants, we have 2 of them, so we got 2 moles of NO. It's going to be at 210.8 joules per mole Kelvin. Plus 1 mole of O2, and that's going to be times 205.1 joules per mole Kelvin. Moles, 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 moles. Okay. And so, well, before we calculate this, do you expect the entropy to increase or decrease? We expect it to decrease because we're going from 3 moles of gas to 2 moles of gas. Negative 146? 0.5. joules per Kelvin. This would be the unit. And so what we see is this says reaction here. The energy says reaction. The entropy says no reaction. So who wins? Well, who wins depends on the temperature. At low temperatures, because when we look at delta G is equal to delta H minus T delta F. And so at low temperatures, the entropy term can be minimized, leaving the enthalpy term alone. And so at low temperatures, entropy term will be minimized, enthalpy term. And so this would be spontaneous at low temperatures.
What exactly is low temperature?
It depends. At high temperature. It varies from reaction to reaction, so we don't know. So that's what we're going to calculate. We're going to calculate what exactly is the temperature. Where's the cutoff temperature where it goes from spontaneous to non-spontaneous? And so at room temperature, this is spontaneous, right? Because the delta G is minus 70.4, so this is spontaneous. And so at what temperature will this go non-spontaneous? It's a question. And so what we want to do is we want delta G to equal 0. Because when delta G is negative, it's spontaneous. When delta G is positive, it's non-spontaneous. And so right now we're negative, and so we want to increase it until it hits 0. And then we want to further increase it so it becomes non-spontaneous. And so we're somewhere here, and we want to increase the temperature so that delta G goes to 0. And so in order for delta G to go 0, what has to happen is the enthalpy term has to be canceled out by the entropy term. And so let's say I have driving force here, which is minus whatever it was, minus 114.14 kilojoules. And I have non-driving force here, which was, this is a negative times a negative, it's going to be plus whatever. And so I got to get them to cancel out the two terms. And so this is, one thing I could do is just solve for t, right? So if I solve this for t, t is going to equal, and so we can just plug that in here. Delta H is minus 114.14 kilojoules. And delta S is minus 146.5 joules per Kelvin. And then we got to get the units the same. So every kilojoule is 1,000 joules here. $963.13 Kelvin. And so let's see if that works out, if that temperature is enough to cancel out the delta H. And so my delta H is minus 114.14 kilojoules. This is going to be minus a T. The T is going to be 963.13 Kelvin times my delta S. My delta S is minus 146.5 joules per Kelvin, and then convert it. I could either convert that into joules or convert this into kilojoules. Let's convert this into kilojoules. Okay.
So we got
779.1.
Because we did this one last week, but instead we got delta H 141. Let's do cut that down. Wait, this must be 114.
Oh, we did this last week?
Yeah.
All right, maybe the delta H, I miscalculated it last time or what?
One last time was 141.
All right. All right. If I already did this, then you got the point, right? The point was that we're going to cancel out the favorable enthalpy with an unfavorable entropy. So we just got to make the entropy term big enough to cancel that out. And so any temperature above this, whatever temperature that we get, should convert it into non-spontaneous reaction. And so that's temperature. But we had to make an assumption. What was the assumption that we made? That the delta H and the delta S don't change much with temperature. And so, in summary, delta G can be manipulated or can be changed with temperature. And we're doing delta G standard. And so delta G standard at temperature T is going to be about equal to delta H, well actually it is equal to, let's do that first. Delta H standard at temperature T minus T delta S at temperature T. But we don't have temperature T, and so what we do is we assume this. We assume that this is going to be about equal to delta H at 298 Kelvin minus T delta S at 298 Kelvin. And so we'll say this, as long as the phase doesn't change, and the phase is the state, solid, liquid, or gas. As long as the phase does not change, then this is okay. Okay assumption. All right, the next thing we're going to do is this. Standard means what? One molar and 1 atmosphere or 1 bar. But what if we were under non-standard conditions? Delta G and T. If we're under non-standard conditions, then we would need this. And so delta G is going to equal delta H under non-standard conditions minus T delta S under non-standard conditions. And so could we say this? This is going to be at temperature T, temperature T, temperature T. Well, we could say this, that the delta H under non-standard conditions doesn't change much from 298 with temperature. So we'll just say this is going to be delta G at temperature T is going to be about equal to delta H at 298 minus T delta S at 298 Kelvin. Okay, this is okay. Okay. But what about this? Can we say that delta H under non-standard conditions is about equal to delta H under standard conditions minus T delta S under standard conditions? Is that okay to say? This is not okay to say. That's not okay. Well, what if we did this? What if we did delta G under standard conditions at 298 Kelvin? If we did delta G at 298 Kelvin, then that's going to equal delta H at 298 Kelvin minus T delta S at 298 Kelvin. And this is going to be non-standard conditions. And so could I say this, that delta G at 298 Kelvin is going to be about equal to delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin. Is that okay? And it turns out that that's not okay either. And so in order to calculate the non-standard delta G, we need non-standard delta H and a non-standard delta S. And we can't assume that the non-standard delta H and the delta S are the same as the standard, okay, because that's going to alter it. And so we would have to be given the non-standard enthalpy and entropy changes, or the other alternative is we apply correction to the standard. And so delta G under standard conditions, excuse me, under non-standard conditions at 298 Kelvin is equal to delta G under standard conditions at 298 Kelvin plus a correction. And the correction is going to be RT ln of Q, where Q is the reaction quotient. The reaction quotient is just the same as we had before. The activity of G raised to little g, the activity of H raised to little h, over the activity of A raised to little a, activity of B raised to little b. It's the reaction quotient. And so here's where we're going to plug in the new concentrations or new pressures that we have. All right, now we're going to do some more stuff with the temperature. This is delta G at 298. What about delta G at temperature T? Well, delta G at temperature T, well, that's got to equal delta G naught at temperature T plus RT ln of Q. Could we say that this? Could we say that that delta G at T is equal to, well, maybe could we do this? Could we do delta G naught at 298 Kelvin plus RT ln of Q? Will that work? In other words, is delta G under standard conditions at some temperature T the same as delta G under standard conditions at 298 Kelvin? Does that work? This doesn't work. We can't do that because delta G changes dramatically with temperature. In fact, we can get delta G to go from spontaneous to non-spontaneous just by changing the temperature. And so we can't assume that the delta G at some arbitrary temperature T is going to be the same as at 298 Kelvin. And so this is a problem because we need to know what the temperature is in order to solve this problem. Well, that's okay as long as we're given the temperature. All right, we're out of time, so we'll continue this next time.